Hello community! I don't know if you noticed, but a new class of AI has emerged. Now robots do stuff with AI, and language is just an input. Look at those two robots. We have now multi-agents that perform together. And you might ask, interesting, but how can you train an AI complex with multiple agents here that include the robotic task? Well, at the beginning we had our large language model based on a transform autoregressive, and we had three typical phases of the training. We had the pre-training, the fine-tuning with here the supervised fine-tuning, and then an alignment phase with our reinforcement learning by human feedback. Later, when we had the vision language model, we switched to diffusion models with more advanced training techniques. And after the diffusion model, we had the diffusion transformer. And I have some video if you're interested in, because we also moved to video language model if you want. And Sora from OpenAI. In about 5 months, I did a video where I showed you, hey, we can update the technology of Sora to make it even more competitive. But time moved on, and we are talking now in research about vision language action models. And now the latest research shows us that we move back again to the diffusion models as our main architecture. And in the pre-training phase, if you want, we have now imitation learning with the component here of behavior cloning as our main pre-training instrument. And for the fine-tuning phase now we have reinforcement learning based fine-tuning. And you might ask why? Because the complexity is extreme. You have vision, multiple cameras, you have your language model, and you have active interaction with the environment with the robotics. And if you think about one robotic arm, this is nice, but think about multiple. So this imitation learning is now the very first attempt from the research community where you say, hey, this is a type of learning where an agent learns to perform a task by mimicking an expert behavior. Like a human guides now in a first demonstration the robotic arm to show exactly what to do, and this coordinate path is recorded. So instead of learning from scratch, and we have this with our large language model where you have the pre-training, Google pre-trains for a month, and the latest Llama 3 were pre-trained multiple months, half a year. Now, instead of learning from scratch, our agents now, our vision language action agents, learn from real demonstration provided by an expert. And the expert can be a human that shows the robotic structure what to do, or you have a virtual AI or a huge vision language action model that can do the complete environment simulation and the robotic simulation in one run. So you understand, we are now in the research community. We are not talking about Claude 3.5 Sonnet, or will there be, I don't know, a GPT-5. We are much further advanced in the research. And if you want to have a look, I have here in my video where I explained the reinforcement learning based fine-tuning as published by Princeton and UC Berkeley. You see we're here into also some mathematical concepts. And I also showed you with the latest behavioral cloning, we have now fast residual reinforcement learning, and these algorithms were calculated here by MIT and Harvard to address here a different aspect of training robots for some real precise manipulation task. So we are here at AI assembly, where we have a non-controlled environment, and the robot should perform. I told you we have two obstacles we have to tackle with. And this is this precision that is not there. And in this video here, I showed you MIT and Harvard found a way with a residual reinforcement learning based fine-tuning on top of a frozen PC model. They could establish now the precision and accuracy that we need for very delicate operation. Plus, in my very last video, I showed you the second problem that we have in imitation learning, the domain shift problem. There's now a solution with here a particular predicted reward fine-tuning methodology that I introduced you in my very last video. Now, you understand that here, on those bases that we are working with Markov decision processes as our main instrument, and of course, we are working with entropy-regulated Markov decision processes. And I went through what is the definition of an MDP, how do we have to regularize the MTP, what is here our equation, what is here our reference policy that we want to optimize. And then we said, okay, if this is the crucial question in reinforcement learning, how to devise algorithms to solve here the optimization problems, because those algorithms are later used as the fine-tuning algorithms of our new diffusion models. And we went to soft Q function, and we have touched here about here our new toolbox that we have now in AI robotics. But you know, this is all nice and it is beautiful, but the real challenge is if we have multi-agent AI system. Like in my first image here on this video, if you have 4 robotic arms for a medical operation, you have multi-agent system, and those agents have to be coordinated. And I know what you would like to say. Yeah, but we have LangGraph or LangChain or LangSQL or Lang whatever. Or if you want to go here in the trial and error automating phase. Hey, a year ago, or 1.5 years ago, we have DSPy. And just months ago, I think Stanford did here an optimization of text grad methodology that is even better than DSPy. But you know what? No, we want to go a step further. We are in AI research. We are not trial and error. We apply science to the topics. So we have now a multi-agent AI system where we have LLMs, VLMs, VLA systems, and they all work in our environment, and there's a particular task that non-single LLM or VLM can do, but together, the group of our AI intelligence, they can perform the task. So now you understand that we are working here on a deeper level here with a Markov decision process for all of those agents with all of their AI structure, LLM, VLM, VLA, whatever. And now the interesting part is how we do this. How we train this. Now you might say, well, the easiest approach is here. You can see every other AI system in your green environment that you as an active agent are, you simply react to the environment. This is more or less the definition of an agent, yeah? So this is the simplest. You are waiting, looking around, and then sometime when it's time for you to act, you just react. Or B, you as an active agent, you're allowed to communicate with the other AI agents, or maybe just a majority of those AI agents, to inform yourself about their next action. So you can share information with other AI systems in this defined environment for a particular task. Of course, you know, we have multi-agent reinforcement learning, where multiple agents use now a reinforcement learning algorithm in a multi-agent setting, considering action and rewards of the other agents. But you know what? Much nicer is game theory. And yes, you guessed it, in my next video, we will apply game theory. But at first we have to understand the mathematics of game theory, because we are not just looking at the simple form of game theory. We're looking at Markov game. So this will be an extension of our Markov decision process, entropy regulated end-to-end, of a multi-agent scenario where our multiple agents will interact in the same environment at the same time in parallel. And it includes here some elements here as a classical Markov decision process, but with joint action and reward for each agent. And we will build a theory how we can integrate now Markov game theory into our reinforcement learning or imitation learning phase. Now, I think this is so important that starting today, you will find a new playlist on my YouTube. And this playlist is called Imitation Learning of Agent, Advanced RL. And we do this for single-agent imitation learning and multi-agent imitation learning. Because this is really now a complete new branch of AI system. We are not talking anymore about how do I fine-tune my 3.5 Sonnet or what I do with a Mistral Large 2, I don't know what system. Now those things do stuff. And they just are passive in the background, but they are actively approaching you in your environment. So, if you're interested in this topic, my next video will be about the details of Markov game theory. It would be great to see you.